again, hello and welcome to the next episode of VELOVirtual, How to Leave Your Mark with Support-Free Metal Additive Manufacturing. I'm really excited to be here today to talk about this topic as we learn more about our customers and see the types of applications where they are leveraging our technology. We're starting to see clear trends toward certain types of geometries that can generate a stronger business case. And as a designer, you probably have aspirations to change the world for the better, to revise how we do things, maybe even to create a new capability that everyone else thinks is impossible. But at the same time, while you can design your innovation, can you actually manufacture it? And can you do so at the performance and time requirements needed to make that business case? So that's really the focus of today, is unlocking designs that generate the business model that gets you funded, that gets you approved in order for you to leave your mark on the world. So what types of applications, or more generally, what types of geometries are the geometries where support-free generates that business value? And we're going to dive into a couple things today. We're going to talk about the issue of supports, how the use of, or maybe even the overuse of supports is leading to compromises in design and quality. And then we're going to talk about how VELO3D has created a reliable, accessible, and scalable support-free metal AM technology. It is an honor to introduce Will Hastings. Will has over 15 years of design system experience, or is it 16 now?
I guess it's 16 now, so
16 now. So you got to update it. Experience in jet engines, racing cars, and additive manufacturing. Lots of very cool technologies. Prior to being an engineer, he operated nuclear power plants in the United States Navy. He holds a BS in aerospace engineering from Embry-Riddle Aeronautical University and an MS in mechanical engineering from the University of Cincinnati. With over 18 patents, he is registered professional engineer in the state of Ohio, and he is fluent in both English and French. And also Gene Miller. So Gene is a technical sales engineer at VELO3D. A new title for you, Gene. Congratulations. He joined VELO3D in 2016 as a process engineer working on developing VELO3D's hallmark support-free metal additive manufacturing processes. And since then, he has run point on many of the applications that we're going to talk about today. Prior to joining VELO3D, he held various positions in foundry and process engineering, so he knows a lot about traditional manufacturing. He holds a BS in mechanical engineering from Colorado State University. All right, Will, I will turn it over to you.
Outstanding. Thanks for that introduction, Mike. Yeah, so today we're excited to be talking to you about how to leave your mark with support-free metal AM. As a former design engineer, I always, working with future designs, always thinking, how can I break through and advance the state of the art? And there's no better way to do that than metal additive manufacturing. So with that, just a little bit of VELO3D overview. So first off, VELO3D is relatively new to the market. We were founded in 2014, and really we've revolutionized metal AM technology and being able to print geometries that no one else in the world can print, and bringing a level of process control and quality control and consistency really across the fleet of printers that's unparalleled. And other key aspects, so relative to the parts that we work on day in, day out, and Gene will be talking about this later in the presentation, it's really high value parts. Usually we're not dealing with tooling, we're dealing with parts that are flying, whether it's rocket engines, jet engines, or also land-based applications such as power turbines or downhole oil and gas. So a variety of high criticality parts. And really that's where we come alive and where we can shine for customers. A little bit more, as we're also, our suite of products, both software and hardware, are all designed, and the printers, the Sapphires, they are built in the USA in California. So really unique in that respect as well. So for those that are new to metal AM, or specifically laser powder bed fusion, we're going to go through a couple of the staples here before we go into specific applications. So with laser powder bed fusion, basically you have a chamber where you have the powder and you have a part that's being printed. And there's the first step is that you have a piston that basically moves down in increments. For the VELO3D Sapphire, it's 50 micron increments, or 2007 inch, so very, very small layers. And then you have a recoater, which basically applies a fine film of powder at a, we'll say 50 microns in this case. And then afterwards you have a set of lasers up top that are basically coming down and melting the powder onto the substrate itself. And layer by layer, the CAD model that has been sliced is basically produced in 50 micron increments. Bear with me as there's a bit of a time lag. Oh. So if we look here, why are supports needed? So there's a couple different aspects to supports. First off, they're used to hold down the part and to basically control the part from residual stresses that occur during the printing process. So if you think about what we're doing, we're melting powder, melting metal. And so you have very high residual stresses due to, or that are created while the melt pool or the molten metal cools down. And then also the other aspect is for an aspect of thermally cooling the part to try to keep the part or the substrate at a certain desired temperature. So really from a design aspect, a lot of times, if you look at this case here, this is just a nice arch. If you don't have supports and the process is not well controlled, what you'll have is you'll have protrusions that occur, or basically the bending up of the geometry. And so one aspect to that is that you want to hold down this geometry or these lips here of sorts, and basically keep it from prying up and hitting the recoater. And we'll talk about the recoater a little bit later in this presentation. The other aspect is that being able to basically keep the geometry cooler so it doesn't protrude as well. So if you look at some parts and how they're produced conventionally, they're really not a good fit for manufacturing. One of the key applications that we work with a lot of customers on are shrouded impellers. So if you look at this specific impeller here, this is a 0-degree impeller. And you can see with conventional metal AM, they're constrained by a rule called the 45-degree rule. And there's different ways to orient the part in the chamber to try to overcome this 45-degree rule. One aspect would be, and you can see it in red here, these supports are basically all throughout the inside of this impeller. And we'll show the actual part print on the next page. And you'll see how much of a challenge it would be to basically get in there and machine out these supports or break away these supports, because it's a very small area with very little tool access. And then on the second orientation, you basically have the entire impeller oriented at a 45-degree orientation relative to the build plate. And the issue with that is that generally speaking, you want to have round objects like this. So this is a rotating component, and you want to have it flat on the build plate. Cylindrical parts you want to have flat on the build plate like it's oriented in option 1, because that helps cylindricity and circularity of the parts. And that's especially important when you think about balance on rotating equipment. So because of that, this is better from a manufacturing perspective, but worse from a part performance and part operation perspective. So with VELO3D, you can see the solution here is that we don't have any supports on the inside of this geometry here. So, and this over here on the right side of the screen, this is the as printed part. So this is Enco 718 right here. Very robust material, really a backbone of many of the industries that we work with. And you can see very nice surface roughness here. No supports. There's also a bit of a lip here that's been machined down, and that can just be turned down with a or with a lathe, really. So what you get here is basically the geometric freedom that you need. And then at the same time, you have the dimensional stability, or you mean your tolerances, to make sure you don't have an oblong impeller here. And then, another aspect of this, and you'll see this in the parts that Gene's going to be showing, is that we have really a very high surface or very very good surface roughness. So you can see right here, this is a downskin. So this part is being held in the hand over here. And then what you're seeing here on this surface is the downskin at 3 degrees relative to the build plate. So extremely low angles. And you can see it's a very consistent surface. It has a 15 micron SA surface finish, and really a nice quality surface that versus what you get, especially if you break away supports, it looks extraordinarily rough, generally speaking. So very impressive part, just to show the capabilities of what we can do at low angles. And with that, I'll be now handing it off to Gene, who will be talking through several applications to kind of help get your minds going. So take it away, Gene.
Sure will. Thanks a lot, and happy to be here today. Now we're going to take what Will has kind of like set the stage for what we can do, and now we're going to talk about how we put it into practical application in real parts to develop that real business case that Mike was talking about earlier. First and foremost, it's no secret that our parts are part of SpaceX's new Raptor engine. And we can't show any of the parts here due to ITAR and IP concerns. However, we do have componentry flight hardware that is printed on Velo Sapphire that's launched with every Raptor engine. And, you know, without going into too much detail about how revolutionary this Raptor engine is, implementing a full flow stage combustion that, you know, many have tried, but many have failed. SpaceX is actually doing this today, and they're enabled by VELO3D technology with these very complex, very bulky components that are being produced in production on VELO3D Sapphires. This is one that we're really proud of. This is a gas microturbine from Sierra Turbines, where we were really able to showcase the ability to combine parts and print really complex internal features without the need for support material. You really increase your durability by eliminating a lot of these sealing surfaces or assemblies that need to be combined. They were able to increase the power density. The same amount of power is generated with a smaller microturbine, and also a lot of weight savings due to the reduced part count. And all of these features that you see on the right-hand side are printed without the need for support material. We're doing a direct comparison with conventional AM and VELO3D SupportFree technology on the bottom left there. This is all support material that would need to be added on a conventional 3D printer. And it really just doesn't make sense. I mean, you'd have to break this part apart, you'd have to cut it, you'd have to remove this material, and then somehow weld it back together. It's just, it's nonsensical. And really the only option is to print it on a VELO3D Sapphire system with support-free technology and you know, have a successful part, usable part at the end of the day. Next is our Hanwha Turbomachinery for a supercritical CO2 system. This, you know, Will said we could do this. Now this is actually, we did this. We printed this impeller flat to the build plate with no internal support, and the impeller was able to be balanced and actually tested at several thousand RPMs, and you know, and tested successfully. So this is a real useful part, and we didn't have to compromise like you would have to on a conventional AM system. We took this part as designed by the manufacturer and printed with very little post-processing and put right into practical application. PWR Heat Exchangers, another little bit different than the impellers that we were talking about, but this is a very, very small heat exchanger application. This is only about 3 inches by 3 inches by 3 inches cubed. It'll fit in the palm of your hand. And these small little walls here are 320 microns thick. It's very thin for a leak-tight wall, as well as the internal turbulators that actually, you know, stimulate flow through the membranes and enhance heat exchange rate. Those were printed at 220 microns. Not leak tight, but still a very, very thin structure. And, you know, we're going to get into just how that's enabled by our non-contact recoder. But other machines would struggle with this, with these very thin, very delicate features. And because of that, we were able to achieve a 33% lower pressure drop. What that means is better surface finish, less deviations on the inside of these small, very delicate shapes and geometries. And this was also printed in aluminum F357 for PWR. Another application, real application, was KW Micropower's generator housing. We designed this in conjunction with KW Micropower and Topology, and we were able to implement very unique cooling and heating channels inside the bulk of this material. What that did was it cooled the generator so that they would achieve a higher efficiency of the generator during operation, and it also provided preheat to the fuel. So the fuel burned at a higher efficiency when it was introduced into the chamber. There was also weight reduction with this part. We were able to remove a lot of material from the inside. And this was also another case where we were able to combine parts and eliminate a stacking of tolerances between parts that are assembled after manufacturing or production. This is one that we really like to showcase our ability to print large, bulky titanium parts. Those that are familiar with the metal additive world of printing in titanium, titanium prints very, very brittle, very hard, and the likelihood of cracking in titanium is very high. VELO3D has a unique internal stress reduction technique that we apply to the part while it's being printed that actually reduces the internal stress of the part and reduces the likelihood of cracking in the middle of a print. This is another part with very low overhangs on the interior of the part that were printed support-free, and another part where we were able to cut out a lot of weight because it was metal 3D printed and not machined out of a billet. Pressure vessels is another one where Velo technology just really shines. Another part that you just wouldn't be able to print on anybody else's 3D printer. The low angle closeout at the top of this part was printed without the need for internal support material. What you see is what you get. This is a part that came right off the printer. All we did was cut it in half, and that's it. This is highly inaccessible for any support material that would be added. The high aspect ratios of these thinner walls is difficult on a conventional recoder due to interference. The recoder tends to bump and move things around. With the non-contact recoder, we can print very high aspect ratios without the concern of recoder interference. And again, this is a leak type part. It's a pressure vessel, so it's ready for application. So this is a three-part series here in Launcher's E-2 LOX Pump. We printed the inlet, the outlet, and the impeller. We can't show the specifics of the impeller because of ITAR concerns, but it is very similar to our shrouded impeller. This is another application where we printed the impeller flat on the build plate. We're able to post-machine off the external wall. We were able to balance it and actually test it. It ran at 3,000 RPM in cryogenic conditions and was a big success for Launcher. To go along with that, the other components of the pump that we printed were the inlet housing that was out of aluminum F357. That's the part that you see here in the center. And then the outlet housing is in Inconel, 718 Inconel, which is another part. We can't show the inside. However, there is a large volute section in here that would be very challenging or impossible to print on a conventional metal AM system due to inaccessibility of support material, where Velo just doesn't need to add these types of supports. So with that, I will hand it back over to Will, and he'll take us to the finish line.
Awesome. Thanks, Gene. So you've seen a lot of what we can do for you in terms of applications. Now we'll talk a little bit more of how do we do this and what makes our suite of products better than others. So first off with that, a key aspect is that, what's behind the secret sauce. A lot of what it has to do is process control, and how we do this is by having an end-to-end solution. So with our suite of products, first we have the Flow print preparation software. So that's where you pull in CAD CAD models, you orient the model, you add supports if required, and then the part is sliced. That's where the Velo print file is then uploaded onto the Sapphire printer, any Sapphire printer in the world of that material type. And then with that, then there's the assure quality validation software, which is basically where we have 920 different sensors that are being continuously monitored throughout the build process. And it basically gives a level of insight into the build process that is unparalleled with other metal AM systems. And, so we have our own software. We also have the printer itself, the hardware, and finally the quality validation. So by having this closed system or this end-to-end solution, basically we are able to tune our flow software to the Sapphire family of printers and vice versa. And what's really enabling is that we have the software engineers, the applications engineers, the mechanical engineers, all of those engineers are basically in one room, flowing up to one engineering leader, and we can basically tackle any issue out there that is affecting the end process and the part, where with other companies, generally the print preparation software and the printer is two entirely different entities. And it just really makes this barrier of actually being able to control the process and understand what's happening. If we look here, there's also, there we go. First off, looking at our flow software. So what flow does is basically applies the parameters based on the geometry. So if you look at this Sierra Turbines microturbine here, there's a variety of parameters, and we have a much more extensive parameter library than any other solution on the market. So you see right here, there's the bulk core that is applied in the thick areas. Then there's a variety of surface processes. So you see right here, vertical walls, low angle closures, etc. And why we need all these different processes is basically, if you think about laser powder bed diffusion, it's really a micro welding process. So you have a different, just if we think for a second about the analog with conventional welding, based on where you're mounting a part, where you have heat sinks, etc., the thickness of the material, that's basically all those factors boil in together of what the thermal input you're going to have, whether you're TIG welding, MIG welding, etc. On the flip side, if you look at the laser powder bed fusion process, we're basically looking at the thermal environment, because low angle walls or low angle surfaces, they have a much less thermally conductive environment to the build plate versus, say, vertical walls that have a nice straight shot down. So basically we're able to tune the processes for the geometry, and at the same time it's the thermal environment as well. So it allows a whole other level of sophistication and what we can print versus other solutions on the market. Now, another aspect is a lot of the printer, or a lot of the parts that we're helping our customers manufacture, those are critical parts, and the traceability is a key aspect. And the traceability really starts with the print file before a part is ever even pulled out of a printer. So with other metal AM, you have generally a CAD file, then you have to export an STL. You have potential loss in fidelity as you convert it to a kind of a rough mesh. And then those STLs are pulled into the preprint software, and that's where you have a build file. And then for every single machine serial number, for every single laser calibration, you basically then have to go in and update, say, that your beam offset and scale factor for every single calibration. That can be 3 months, 6 months, it depends on the quality plan. But basically you can see that this creates a lot of bookkeeping and process risk, as well as you start to scale up and have metal AM in production. When you have 80 machines out there, this can really turn into quite a mess for those. And it's not just keeping the files straight. If you think about it, what is occurring is that the individual printer calibration, all of the slop in the optics is being taken out with the print file. And if you have a technician who last week he was using print file 5A, for example, and then has a field service engineer come in during his days off, he has to know to use the next print file. Otherwise, he's basically printing in an uncalibrated system. And so it creates a lot of risk of the quality of parts by having a system like this. On the flip side, with VELO3D, we import the CAD files directly into our Flow software for all major CAD software platforms. No STLs are required. And additionally, you have the Velo build file, and then you have one single Velo print file for all Sapphires worldwide. And the way that we're able to do this is that we have a series of routines that the technician, the floor technician, not a field service rep, literally technicians on your floor can, with the push of a button, calibrate the system, whether it's on a weekly basis or before every build, depending on what your build plan requires. And if we take this a step further, when we say one Velo print file worldwide, what that means is, as an OEM, a lot of times there's one in-house Sapphire, we'll say, and that's where the design team is continually iterating on the design to really squeeze the lemon on performance of that specific part, that specific system. Then what happens is the Velo print file can then be locked down, and that Velo print file can be sent to the contract manufacturer and really help the OEM scale up production at a speed that would not be possible if they had to all of a sudden, say, buy 10 or 20 Sapphire printers and then have them installed, qualified, etc. By having this file structure, you can basically scale up your supply chain overnight using contract manufacturers throughout the world. Another aspect to this is the distributed supply chain enablement. So basically, what you have is, with PLM software, most engineering firms out there have a PLM software where for a specific part, there's the CAD file, the drawing file, and then also with VELO3D's technology, you can also upload the Velo build file and then the Velo print file. And you can send that Velo print file, if you have a worldwide PLM, to a family of printers. You can basically have parts printed throughout the world to support your fleet of products. And if you think back to what we were just talking about, of having a different print file for different machine serial numbers for different calibrations, this is basically impossible when you start to try to scale your worldwide supply chain. With VELO3D's technology, it's as easy as pulling down the file from the server. So if we look a little bit more here with the Sapphire configuration, we have the Sapphire and then the Sapphire 1MZ and XC that we'll be talking about in the following slides. So first off, with the Sapphire of today, we have 315 millimeter diameter build plate. That's full usable space, and there's no keep out zones due to gas flow or any bolts on the top of the build plate that you have to stay away from. It's a round build plate because a lot of our customers are building round objects as well, so it actually works out quite nicely. And then it's a dual laser system, and we have full in situ overlay calibration. It's a little bit deep for the talk today, but you can certainly contact VELO3D if you're interested to talk about this capability some more. It's quite impressive. Each laser has full field capability. And while we have full field capability, generally you want to still print directly underneath the laser. But we've designed a system to have that full capability. We'll talk about materials on the last page, and then our standard parameter set is 50 microns. And another key aspect is the proprietary non-contact recoder. And talking about this a little bit more, so with a standard recoder, it's basically kind of acts like a snow plow. You have one piston going up, one piston going down, and it basically kind of drags across the powder layer by layer. With VELO3D's proprietary non-contact recoder, it's a three-part system that all happens in one single pass of the recoder. So first off, a considerable amount of powder is dispensed onto the powder bed. And then at the same time, there's the recoder, the hard recoder blade that basically evens out and provides a consistent, or we call it the normalizing blade. It basically provides a consistent thickness. And then finally, we have a proprietary powder removal system that basically takes out the final amount of powder so that you have 50 microns of powder remaining. And this is really significant because if you're accustomed to traditional laser powder bed fusion, recoater clashes or protrusions are the leading cause of failed builds. And so by having this, non-contact recoater where we can have protrusions in the 600 micron to 900 micron range without having a failed build, and actually being able to do that consistently is really an advantage. Another aspect is as you print to lower and lower angles, there is going to be more and more protrusions. So our software accounts for this, our processes account for that, and basically allow us to print at lower angles and not have recoater clashes. So it's actually key in terms of our first time yield, in terms of our consistent yield in production. It's also a key aspect of being able to print at low angles. So really it's at the heart of one of the key things at the heart of what we do day in, day out. Another really exciting feature, and I personally, this is one of my favorite technologies that we've developed in-house, is the height mapper. So if you look here, it's basically a 3D topographical map of the powder bed that we have before and after lasing on each layer. So you can see right here, this is a lased height map when it's business as usual, no issues there. You can see green is nominal, yellow, red is high, blue is low, or valleys, so red is peak, blue is valley. And then you can see what happens if a protrusion occurs. So we have this topographical map, and then we have analytics running simultaneously. And if there is a protrusion, and you can see right here, it's beyond 500 microns, it starts to turn black and white when it gets to the extremities. What it does is it basically pauses the recoater and the build to prevent a recoater clash from occurring. And this red circle right here, this isn't created in PowerPoint. This is actually created by the analytics. So the analytics will show the technician, hey, this is where this protrusion happened. You can see it visibly, not only from the topographical map, but it also shows where the error is occurring. And then if you look, talking a little bit more about Assure. So there's several aspects to process control. The first aspect is ensuring that the tool is well calibrated. So when we talked about calibrations earlier on, we have this tool health checklist that basically has 5 different parameters or 5 different areas where we perform calibrations on the system, or I should say it's really the technician on the floor with the pushable button on the screen, on the home screen. And then you also have these lased images that are part of that. They're all uploaded onto the Assure server. And then finally, you have control charts. So there's several control charts. This one is the peak height, where we're looking at the peak value as a function of time or layer. And you can basically see if there's any abnormalities in high protrusions that are abnormal during the build. We also are monitoring humidity, oxygen content level, hopper level, etc. So we're basically looking at the key factors that need to be controlled during the process. And all of this data is post-processed and viewable on a dashboard by the technician and manufacturing engineers. And then finally, all the key data is wrapped up into a PDF called a Assure build report. And with this, you can then send this to the customer, and it can be used in the quality management system for that part. One key note about material properties. So generally speaking, the mechanical properties are better than cast and approaching wrought material or forged material. The density is 99.9% coming out of the printer. And then, if you compare this to, say, castings, where generally 95% dense is the kind of the ballpark that you can see, or the requirement that you can see, it's tremendously more dense. And just, one note to back up for a second, the reason that we're able to get better mechanical properties, if we look at tensils, for example, it's because you have a finer microstructure than castings. And so that drives the better material properties. And then relative to geometric accuracy, so on small objects, we say plus or minus 50 microns or 0.002 of an inch. And then there's also this thermal aspect of it. So there's residual stresses, and then there's also the aspect of the cool down of the part as it, the hot part cools down, and that accounts for another 0.2%. So if you have a large part that is printed, a lot of times some of the inner diameters can be undersized, and so you can compensate for that by scaling the part very slightly. And then also the data sheets are available on our website. And if you have any other questions about the materials, you can always contact us at VELO3D.com. A little bit more about the part volume evolution. So this is the family of sapphires we have and are developing. So first off is the sapphire that we talked about already with 315 millimeter build plate by 400 millimeters tall. So this is for in the inches, that's about 12.4 inches by 16 in diameter by 16 inches tall. We then have a 1 meter Z option that's available for certain applications where long parts are required. This system has all the same bells and whistles as the Sapphire, just with a larger elevator or longer elevator. And then additionally, we have the Sapphire XC. So this is a very exciting machine. It's an octo laser, 600 millimeter diameter build plate, 500 millimeters tall. And that's first one is being delivered fourth quarter this year, and then we'll be ramping up shipments very quickly in 2022. A lot of interest just because this size really it increases the number of parts that can be printed. And then also another aspect is with the larger system is it also has 4 times more lasers. So if you look at the part cost today compared to the part cost on the Sapphire XC, it's about a 65% cost reduction just because you have a much faster throughput on that printer. So very, very exciting, both in terms of increasing the family of parts that can be printed not only for size, but also, cost is a key aspect and a lot of times one of the key barriers for metal AM parts. And then another aspect with VELO3D is, so we generally do not print parts internally. We focus on developing the world-class software and machines day in, day out and processes. So we can connect you directly to our contract manufacturing partner network. So you can see them listed on the page here. And we support you through them continually day in, day out. And then one final question that we often get is what materials you have available. So in terms of high temperature alloys, we have Inconel 718, Inconel 625, and Hastelloy X. Hastelloy C22 has excellent anti-corrosion properties for certain applications with some pretty corrosive chemicals. We also have Ti-64, titanium 64, and then also for aluminums, we have F357 aluminum, very similar to A356 aluminum, which has been used in industry quite frequently for decades. And then also for high strength aluminum, we have Scamalloy. And then relative to materials that are being developed, we have GR COP 42 that's under development, stainless steel CA6NM, which is popular in the energy industry. And then finally, we have Haynes 282, which is another high temperature, high strength nickel superalloy. Very exciting material that a lot of customers are asking for, and we're going to have developed at the end of this year. So with that, I'd like to field some questions.
All right.
So take it away, Mike.
Yeah, thanks, Will. And thanks, Gene. One of the comments with regard to the support-free process, there are actually a couple questions here. Does it use the loose powder as a support? Is that what we're doing?
So I would say relative to using the loose powder as support, we are able to print objects free floating, which is not connected to the build plate. In that case, it is somewhat acting as a support. But if we go back to the purpose of supports and, the usefulness of them, as we stated, it's really to help hold down the part and keep it from curling up from residual stresses. So in that case, the powder is not able to act. And then the other aspect is thermal, basically to help the thermal stability of the part. And in that case, the thermal conductivity of powder isn't as good as the substrate. So it provides a slight amount of thermal transfer, but not too much. So it's really not the same use, I would say, relatively speaking.
There was also a question, you mentioned kind of these free floating parts. Can you talk about that a little bit? And also, would that enable stacking of the parts or nesting of the parts?
Yeah, that's a great question. So with free floating, we're able to print parts completely not connected to the build plate in very certain applications. For most, if not all the parts you saw today, they were printed with connections to the build plate. It's something that is available for certain geometries where it lends itself. And in those geometries, you can basically nest many parts in one build, and it really helps in terms of ramping, high rate production, having builds go on for days at a time, and really increasing machine uptime and utilization. So if you have parts where you're interested in that, we do have some webinars as well. And I would say as well, feel free to contact VELO3D to see if your specific application lends itself for that. But it's certainly some to consider early on in the design process versus wait till the last minute and then try to see if it can be printed free floating.
Yeah, and I would say there are a couple questions here on specific applications. So most geometry related questions will depend on the actual design of the part. So if you're really interested in diving into that and getting some consulting on that, you can get in touch with us at info@velo3d.com. It's a free evaluation. So, no charge evaluation, but we'll take a look at that and happy to provide feedback on those parts. So if you do have any questions about that, including other metals that we didn't mention in this session, I'd include that in that as well. There were a couple questions in here on the Gene. I think you had a slide on there with a big titanium disc. There's some questions in there about the in-process stress relief. Now, I understand this is proprietary process, but to the degree that you can talk about it, they're wondering more about it. And does that remove the need to do stress relief after the process is done?
I can shed some more light on that. I can't divulge any IP without something like an NDA in place. However, I can say, ultimately, no, it is not eliminating the need for post-processing heat treatment. It's not designed to reorganize the microstructure or provide a significant amount of ductility to the titanium. It's still brittle when it comes out, but it's less brittle. I can say that, we are not heating the build. We are not putting some extra tool in there or heating device. Everything that we do is, what you would expect to find on a conventional metal 3D printer. However, anything more than that, I can't really divulge in this venue. We'd need something like an NDA to go into details of what we're actually doing. But there's no special sneaky, extra heating device going on in the chamber during printing.
All right. There's some questions on aluminum F357. And the question is that significantly alloyed with anything, or is it mostly pure aluminum?
Sure, I can take that one. So generally speaking with aluminum, it is an alloy. It's ALS, the actual content is ALSI 7 Mg, so magnesium and silicone. So it's a lower silicon content than some of the powders that have been used in the past for laser powder bed fusion. But yes, if certainly can look on our website if you have any more questions about that, or contact us directly if you have questions about the chemistry.
Do we offer any prototyping services?
Would you like to take that one, Gene?
Yeah, sure. So that's something that we do very often for customers who are interested in printing parts, especially on a production level. Do we print one-offs? Our contract manufacturers do. If it's a simple part, we're happy to put you in touch with them if you would like, a prototype of something printed. If it's something complex, we're always happy to lend a hand and offer some design for manufacturability consultation if needed. However, for prototyping, you probably want to go directly to our contract manufacturers, and they can provide you a quote and a quick turnaround. But for Velo internally, we're more focused on producing the 3D printers and then enabling business for our contract manufacturers.
Well said. There's a question here on the order of magnitude associated with build times that would utilize the full Z height of the printer. And I know it would depend on the geometry, but is there sort of a roundabout number?
Of how long a full build height build would take?
Mm-hmm.
That is completely driven by the geometry that you're printing. If you're printing something very quick, and the quickest layer time that we can do today on a Sapphire or Sapphire 1 meter Z is about a 20-second layer time, and that multiplied by about 8,000 layers. That would be the fastest possible build. However, if you're doing something larger or more massive, it's going to take more time to process that material on every layer. And I mean, I've seen some really beefy parts that take a long time to print. So, it's really driven by the geometry. But yeah, the minimum would be around 8,000 layers times about 20 seconds.
A question here with the SupportFree process, how do you prevent heat buildup when the part is not attached to the build plate?
Yeah, so there's an aspect of the, I would say when you have lower angle processes, you have less thermal input, and our low angle processes are much more sophisticated than just dialing down the laser. So we use sophisticated algorithms to apply that process. So that's, I would say at a high level, there's this aspect of, there's certain geometries that that lend itself to it, primarily, starting from a single point is the first aspect. And then beyond that, there's a parameter in flow that you can apply for free floating start. And then beyond that, apply, or the flow software will take over with the correct processes and go from there.
And I might just elaborate. That's one thing that Will mentioned earlier. There are good candidates for free floating, and then there's candidates that just don't make sense. And for large, massive parts where we're going to be putting a lot of high energy into, they don't tend to dissipate the heat as well. So we would probably opt for direct contact to the build plate on a large part that's going to generate a lot of heat.
Yes, that's a great point, Gene. And I mean, that goes as well as when you start to get into very sophisticated parts, you want to make sure you're not thermally choking the part with having a ton of mass up top. Very, not much of a conductive path to the build plate as well. So it's, yeah, good point.
There's a question here. What are we doing for material property characterization? And can you talk about that work?
Sure, I'll take that one. So relative to material characterization, we're focusing on MMPDS as the route for that. So we're the first company to submit data for, first laser powder bed fusion company to submit data for MMPDS for AMS 7038. And the reason we do that is because for many entities, just having the data isn't enough for their authorities. With MMPDS, it's recognized by NASA, DoD, and the FAA. And so it's a reference, it's data that's analyzed and approved by a third party, Battelle, and it's presented in a forum that is part government agency, part industry, and part material producers such as VELO3D. So because of that, we've taken that route and really used that as kind of the primary source of material characterization. So great question.
And there's a question just trying to clarify when we talk about these specialized parameters for different features, what would be in the scope of that? Are we talking laser power and speed, scan strategies? Like what's in the scope when you talk about those recipes?
Yeah, talking about characterizing our different laser processes based on levels of overhang. It's a question we get a lot, and it's something that we have, some unique testing characteristics and testing data based on these criteria that are usually driven by the customer or the end user. And we have quantified that data based on certain levels of overhang, levels of different low angle skins, and I can share a data set if someone is curious as to what that means and does, but we don't see a big degradation for material properties in these low end. That's based on tensile data and fatigue data.
That I think they're talking about more of the process that's, when flow sort of slices and dictates a process. When we look at those recipes and those parameters, what would be included in that? Is that just looking at laser power and speed, or are we including scan strategies and other things as well?
Oh, we can't divulge that. That's our bread and butter right there. We're doing some very unique things with the lasers as far as powers, focus. I mean, we're doing a lot of unique stuff that people are just not really exploring or utilizing yet, and that's something that we would not divulge.
So to say it's highly sophisticated would be an understatement.
Yeah, we can provide data of the tensile properties or mechanical properties of these processes, but we keep those very close to the hip. Those are not shared.
Okay. Is there any productivity trade-off to enable support-free processes? Like, would you just use it all the time, or are there times when it makes more sense to use supports, or like we mentioned before, mount to a build plate?
Yeah, that's a good point. Support-free is the low angle skin in particular is a slower process than just printing bolt core, and in some cases it does make sense just to add support material, especially if it's something that's easily accessible or easily removed after the print is out of the chamber. It's something that we would address on a part by part basis, and make our consultation with that consideration. So if the customer would prefer to just print something fast and doesn't care about the surface finish and can easily remove supports, we might just add them. But if they're impossible to remove, yeah, you bet we're going to use that low angle process and really let Velo shine.
Yeah, maybe one thing to add just relative to that question is we're not doing any like long build pauses at the end of layers. I understand that's attempted and with some other laser power bed fusion systems out there. We don't do any of that. We're not forcing long build times or pauses at the end of layers to try to help the part cool down. We address the issue by just tackling it head on, having a sophisticated process that controls the thermal input while the powder is being lased. So it's we're not doing weird stuff in the back room.
Very cool. Well, we're about up on time, so I just wanted to give you each a chance. What are your closing thoughts around these types of applications? What are you seeing in the market with customers? And then how can people best get in touch with you? And Gene, if you want to kick that off.
Sure. From this presentation, I just got to say, the proof is in the pudding, and the parts speak for themselves. I've seen a lot of other hype out there based on what we say we can do. When you actually print a part and put it into actual application, that's when it's indisputable proof. So really, to have these parts and these wins is really exciting, because it's proof that we are changing the industry and leading our manufacturers into new ways of thinking about making stuff, really. So really excited to see this move forward. And info at VELO3D. Check out our website. You can get a hold of me or one of our other sales engineers or an applications engineer pretty easily.
All right, Will, to you.
Yeah, I would say, again, we're always excited and impressed with what our customers are bringing to us with these sophisticated designs. I'd say some of the general underlying themes is a lot of times where it makes a lot of sense is when there's significant part consolidation and also fluid flow involved for even more complex three-dimensional surfaces. So keep that in the back of your mind, and certainly feel free to reach out to us at VELO3D.com. And excited to be seeing what designs will come and how we can help you change the state of the art.
Awesome. Well, thank you everyone for joining us today. And that concludes our session. Stay tuned for lots of great applications and stories.
Take care, everyone.
Thanks.